This is 25.1, electric current and changing electromagnetic field, or magnetic field. Today we're going to talk about electromagnetic induction. We'll look a little bit about motors and generators, and we'll look at alternating current and direct current. So let's define electromagnetic induction. Induction is when magnetic field is produced without a magnet, or current is produced without a battery. So it's when induction is when something is produced that it would normally not be produced. Now usually we get current because there's a battery which changes the potential difference, which causes the electrons to move, which makes electricity. Or with a magnetic field, we have a magnetized piece of metal, and that attracts magnetic things. So we can produce these things without having those two basic needs. In order to induce a current, we need a closed circuit wire, so just a loop of wire. It's completely closed. Let's say that loop of wire is hooked to a light bulb, and we have to move it through a changing magnetic field. So here is a couple of examples of how to do that. Let's say that we have a nice big magnet here, or like the North Pole magnet. Well, I guess it's north and south. Let's just say positive to negative here. And we have a nice magnetic field. Somehow it's produced. Okay, and then we have our loop of wire, which you have to excuse my loop of wire. It looks like one of those ring pops. Let's say we have it like that. Here's my light bulb with wire connected to it. Now what I would do is I would drag the wire down through this magnetic field. And the light bulb would light up as it enters and as it leaves. Because that's when it's changing. When it's in here and it goes from here to here, it's not changing. It's a constant magnetic field, so it's not going to light up. But as it moves from having no magnetic field to having magnetic field, it'll light up. And then as it goes from magnetic field to no magnetic field, it'll light up. Because again, it's that change in magnetic field that will cause the electricity or the electrons to move through. And that makes sense, right? Because when it's moving through here, the electrons are all being pushed one way. They'll be pushed like this way. And then once it's in here, they're stuck. And then once it's going out, they move the other direction, right? Because the magnetic field is pushing it in the opposite direction. So as long as the electrons move, you get that electricity, and they're only going to move if the magnetic field is pushing those electrons around. Now let's look at another couple of examples. This would be a constant magnetic field. However you would set this up, this would not actually be two magnets. This would be something else. Let's look at like my little circular magnet that I have stuck on the board here. Here's my little, it looks like kind of a circle here. If we draw magnetic field lines on it, the closer you get to it, the stronger these magnetic fields are going to be, and the further away you get, it's like an apple. So we could take our little loop of wire, our little light bulb, and we could drag it through this magnetic field. So it starts out with a weak magnetic field, and it gets stronger and stronger and stronger, and then it gets less and less and less. So this one will light up the whole time as long as it's moving. If you stop, now no magnetic field because you're not pushing the electrons, they're just stuck there. So as you move it in and out of the field, the bulb will light up. Okay, to induce a magnetic field, you need to have a constantly changing current. So your direct current is only going to produce a magnetic field when you first turn it on. But if we have a current that changes, like alternating current that goes from one way to the other, as long as it keeps changing, it's going to produce a magnetic field. And that's where you use that right hand rule. So let's say this is your wire, and the current is going in this direction. As long as it's alternating current, you're going to have a magnetic field. And this magnetic field will be, and use your right hand, thumb is in the direction of I, it will be this direction. So behind it, and then thumb up to it. All right, since there's no actual battery hooked up to this current, to this light bulb, it still has a voltage though, because it has current, so it has to have a voltage. But that voltage doesn't come from a battery because it's not really a potential difference. It's the magnetic field pushing it. So we call it the electromotive force. Right? The magnetic field is moving these electrons around, so as you move through that electric field, or the magnetic field, it produces a current which causes a voltage. And this voltage works the same way as a battery voltage. We just call it EMF instead of V. So anytime you see EMF, you can pretend it says V. Big V for voltage, for potential difference, yes.
So does that mean the light bulb only turns on if you're moving it? Like if you just...
Yeah, it has to move, because it has to be a changing magnetic field. So it either this has to be moving, or you could hold it still and have the magnet move. So you could like spin the magnet around. But as long as that magnetic field changes, then you'll have the current. And if you have the current, you'll have this EMF. And notice that it has to have a magnetic field, the length of the wire, the velocity of whatever's moving through it. So if you're moving the loop of wire through it, or if the magnet's moving. And then we have this sine theta. Now, in your questions, if it does not give you a theta, you can use 90. If it says parallel to, then it's 0 degrees. If you put 0 into that equation, you get nothing. So if I were to move this loop of wire here on the first one, if I moved it horizontal with the magnetic field, nothing's going to happen. But notice that I moved it down and the magnetic field's to the right. So then that would light up. But if I moved it this way, nothing. So it has to be somewhere between 90 the max and 0 would be min. So anything in between is going to be some portion of that. Well, that's where the 90 theta comes from. Yes?
And if you say they don't give you one, you just assume it's
you assume 90.
Oh, it's 90.
Yeah. You assume that it's maximum. It's a lot like the torque equation. You guys remember FR sine theta? When you open a door, you always want to open a door 90. So if this is my door here, I always want to push on it like this to get it to open. I would never push on it like this to open it. It's not going to go anywhere. But this one's going to make it swing. So the same thing with magnetic field. Oh, questions about this yet?
Yeah.
Okay. So why is this important? Why do we need induction? And that is because it is how we generate our power. This is what electric generators work on. They use magnets and they use this inducing current. So if you could continue to move this light bulb back and forth through this magnet over and over again, you'd be turning your kinetic energy into electrical energy. But it gets tiring doing that. So there's a couple other ways we could do that instead of just standing here with our arm and going back and forth. So what they've come up with for, a couple hundred years now, we have a magnet and you have a loop of wire. And this loop of wire is hooked to something that's going to spin it. So that could be you. You could be sitting there with a crank spinning it. You could be hooked up to a bicycle. Or even better, you could hook it up to a turbine. And the turbine can move because of water, right, running water, or wind, or a bunch of hamsters. That'd be fine. Hamsters, hamster power things. Exercise the hamster. All right, let's draw this on the board. Let's see how this works. We have a North Pole magnet. Obviously, it would keep going, and you have the South Pole on this side. And then over here, you have your South Pole and your magnetic field from north to south. So this is our magnetic field. Now we have a loop of wire, which they call this a split ring communicator, I believe. So use your right hand rule. If the magnetic field is this way and the force is down, so as we spin it, we force it down, force. So magnetic field, force is down. Which way is the current? This way is my magnetic field, this one. My force is down. Which way is the current? Current's your thumb. It's up. There we go. So that means that the current flows this way. And on this side, remember we're spinning, if this side is down, then the other side has to be up. Right? Force is up. So if the force is up, and the magnetic field is still this way, so force up, magnetic field that way, which way is the current?
Down.
Down. So you get this flow of current. And as it twists, this side moves over here. So now the force is down and the current is in the opposite direction on this side. So what happens is the current goes from this way to this way, to this way, to this way as it spins. Every time it spins, it flip-flops. So that's where our alternating current comes from. Now, you worked with direct current before. It was very easy. And the electrons just kind of chug along in one direction. But with alternating current, the electron goes from here to here to here to here. So the electron doesn't actually move very far on the wire because it keeps getting pushed back and forth. So how can the electron not move very far, but we still get electricity flow all the way through the circuit? Because what? No? Anybody want to take a stab at it? Even though the electron doesn't go all the way around the circuit, how can the electron go just back and forth, and yet we can still get electricity through the whole thing?
Because when it goes down, it stops.
So what's the electricity produced by? They do bump each other, yes, and you're getting closer. So this electron moves, and it creates, whenever an electron moves, it creates an electromagnetic field, like a light wave, right? Except for it's not a light wave. It's a different type of electromagnetic field. And that electromagnetic field causes the next electron to move, which creates an electromagnetic field. And that creates the next electron to move. So as this one moves, it bumps the next electromagnetic field and causes a pulse, electricity.
So like a domino effect?
Yes, but with electromagnetic field. So that's how when I turn the light bulb on, it doesn't take 10 minutes for this whole room to light up, because it's transferring it as an electromagnetic wave, which moves at the speed of light. So it moves pretty close to the speed of light in a circuit. So when we turn a light switch on, the whole thing goes almost instantaneous. Yes?
What about, like, does it take longer when you go overnight when it's, like, that long period as opposed to, like, in between classes? Because, like, during fourth period, don't you, like, keep your lights on and things like that?
Mm-hmm.
So wouldn't it take longer in the morning?
Mm-mm.
Because it's, like...
Nope. The electromagnetic field, it moves at the speed of light, and it's gone at the speed of light. So as soon as it loses power, it can't save anything up, unless there were batteries in each of the lights that were recharged every time we did it. Then it would happen. But nope, shouldn't have.
Is that why, like, stadium lights take a while?
Stadium lights, they do take a while, but that's because the filaments are starting to glow more, I believe. They're weird lights. I don't know that much about them, but I know that they need to charge a little bit more. Okay, so we have this. It's hooked up to a turbine, like the ones in a generator, like your water, your dams, right, or your wind turbines. And these loops will rotate, and as they turn through the magnetic field, it goes from current this way to current this way. So you get that alternating current. That means it's going from maximum current to minimum current, and then back to maximum current. So this flip-flopping creates this fluctuating current, which we call alternating current. I really do have a slide, I promise. Come on, computer. You can do it. I hate this one. Oh, it's thinking. All right, so this alternating current, depending on how fast the thing is spinning around, will determine the frequency of this alternating current Most of the time you'll see a 60 hertz frequency of alternating current, which means it changes direction 60 times a second. So it's pretty much spinning around 60 times in 1 second. That's pretty fast. Now, because of alternating current goes from max to min, we have to use more of an effective current, which I'll teach you how to do in just a second. But this alternating current is much cheaper to send it to your homes than would be direct current. So even though direct current, the math is easier, and Thomas Edison was like, direct current is much safer because it's much lower voltages, alternating current is cheaper for us to go because put across the country because our power lines only have to be like this big instead of like this big. Right? So that alternating current keeps it moving. Here is the equation for effective current. And again, the effective is what the current is that we can actually use because it's going from max to min. So it's kind of like your average current, but that's not quite right because it's going from this way to 0 and back to this way to 0. So it's going to be the square root of 2 over 2 times your maximum current to get your effective current. All right, are we ready? The effective voltage is the same equation, just with voltage. And then notice that we're going to use P equals IV for both the max, where we have maxes under each of them, and then P average is I effective, V effective. And you're going to need these equations for your homework, so if you didn't write anything down today, you should probably write that one. Okay, I have a practice question for us before we start our clicker questions. This practice question says, calculate the effective voltage if the maximum voltage of the generator is 240 volts. So we're given 240 volts. What is this? What is it? Max what? Voltage. There we go. Okay. And what are we looking for? What is it? IMAX. No. Try again. V effective. Close enough. Calculate the effective voltage. The first one, sorry. Okay. This is going to be the effective. Oh, I have it written right there. I'm not going to write it again. Plug it into the green equation up here. Yeah, C effective equals square root of 2 over 2 times 240. And I got 169.7. We'll just round that to 170. Now the next question is a little bit tricky because I've put this 100 watt light bulb all the way down here. But assume that the P max is 100 watts and that will let you find I max. So I've just told you that P max is 100 watts. And what are we looking for next? Next question. Second one, I max. What is the maximum current? What equation do we want to use? I'm looking for I max. We got P max. We got V max. You guys are not awake this morning. Kind of sad. How about this one? Yes. So 100 equals I max times 240. Now I have 0.417 amps. Now that we know I max, we can find effective current. So we'll use this one. I effective, square root of 2 over 2, 0.417. And I have 0.293. 293. Last question. What is the average power? What's the equation for average power? You guys wrote it down. Say? Okay, good. P average equals V effective, I effective. Did it out of order, but that's it. So P average is going to be 170 volts times 0.92293. I can't do that today. Not working for me. And that gives us about 50. Okay, you guys ready for some clicker questions? Let's see if I can get them to work. They were broken today. Here's our first question. What is the effective current generated by an alternating current generator? So all you have to do is pick the right equation. Now, my computer is still loading, so don't try to answer yet, but you can look at it.